Hi, in this video, we're going to talk about the mathematics of estimating a logistic regression model. All right, so we're specifically going to focus on the logit-link function, but this will work for, conceptually, this can be extended to other link functions quite easily. Now, our approach is that we're going to do maximum likelihood estimation. All right, so our likelihood function is on pencil and paper the same as our probability function. So when we have a probability function, the random variable x is the variable and the parameters are the constants. Okay, so now we're going to reverse it. All right, so this is after I have observed data. What I'm going to do, I'm going to take that same function I just had for a probability, but now I'm going to treat the x's as constants. I'm going to treat the parameters as the variable. And so now my x is my observed data. Those are constant because I've seen them. I've recorded the values. And I've got a function on the parameters that corresponds to a probability. Now, this is post observing data, so this is no longer a probability because it's already happened. Now we're going to call it a likelihood. All right, now what we want to do to figure out our model for our logistic regression model is that we're going to take the coefficients that maximize that likelihood function. Okay, and so what we're going to do? Well, we've taken Calc 1. Calculus is easy for us. You know what we're going to do? I am going to maximize that function using first derivative, and I'm going to take a second derivative to make sure that it's a maximization, and boom, I've got it. Almost. It's the right idea, my friend, but there's a problem. There isn't going to be a closed form for this derivative. And we're going to have to use an iterative process to estimate that maximization. All right, so let's dig into this. Let's have some fun. All right, so first thing I want to talk about are the distribution functions in R. All right, so the distribution functions, overwhelmingly, there's a few packages that deviate from this, but overwhelmingly, you have D, P, Q, and R for our distribution functions. All right, so what we're going to do, so the star indicates the different distributions that we want. So this could be norm for normal, could be gamma for gamma distribution, could be binom for binomial distribution. That's what we're going to look at. D is for the probability density function or distribution function. All right, so if I have a discrete random variable, this function will give me the probability of observing the x given the input parameters. All right, now if I have a continuous random variable, then it's going to give me the value of the function that we use for integration to get the probability of an event. Now P is for the cumulative distribution function. All right, and so that is the probability of less than or equal to the value that I put in. Now the next one is the quantile function. All right, so this is if I have a continuous random variable. This is going to be the inverse of the cumulative distribution function that we talked about right up here. Now, when it's a discrete random variable, there's different ways to compute the quantile function, and you can specify in the function how you want to be computed because of the fact that if it's discrete, there is not a perfect relationship. If I put in a probability that's between levels for the cumulative distribution function. So there's a couple different ways to go about it. It usually isn't a big deal. I haven't had to ever tinker with it at work. And R is for random number generation. And also, okay, here is a statistics joke for you. What's a pirate's favorite letter? R. What's a pirate's favorite programming language? R. All right, so good dad joke for you right there. All right, so now if I'm going to be doing the Bernoulli distribution, I'm going to end up using the binomial distribution. And so here's the example of the probability density function in action right here. This D star, here's D binom. All right, and so the binom is taking the place of the star. So that's to indicate that I want the density function for the binomial distribution. Okay, so the Bernoulli distribution, this is the distribution we use when we have one event and there are two possible levels. So this is the simplest random variable I could possibly have. To make things easy on ourselves, to code things simple, we're going to denote zeros and ones as our two possible outcomes. We have two different levels, 0 and 1, that's it. Typically, we put 1 as a success, 0 as a failure. But one could also be could be positive for disease, could be the positive for pregnancy, positive for an earthquake. Success doesn't have to be a necessarily a good thing. It's just that in the math labeling, it doesn't really matter what we label it as. We just have to have coherent mathematics, and we just call it a success as our global overall term. All right, well, there's a probability of getting a 1, and let's go ahead and call that P. All right, well, I've only got 2 possible events, so the probability of that 0 has to be 1 minus P. All right, so our probability mass function, or probability density function, is going to be P to the power of the random variable times 1 minus P to the power of 1 minus the random variable value, where we get 0 or 1 in here. All right, so the probability of y equals 1 is exactly P if I plug in 1 into this, and the probability of 0 is 1 minus P if I plug in 0 into this. Our expected value, well, if you sit down and compute it, is just P, and our variance is P times 1 minus P. Okay? And so something that you'll notice, if I go through do my college algebra and distribute, I can represent it as this is a quadratic. I'll see how a vertex at P equals 1/2. We have maximum variance at P equals 1/2, variance of 0 if P is equal to 0 or 1. All right, so let's go ahead and just run through some code just to get a feel for it. So here is the density function for the binomial distribution. And now here I'm saying 1. So I only have one event. When we do Bernoulli distribution, we only have one event. That size equals 1 for that. And here I'm going to go ahead and just put down that the probability of success is 1/2. Well, what's the probability of 0? What's the probability of 1? Well, it's 50-50. I built it up that way. Now here, this is the cumulative distribution function. So I want the probability of being less than or equal to 0, probability of being less than or equal to 1. All right, for the same distribution I just had a moment ago. And you can see it's 1/2. I have the probability of 1/2 for being less than or equal to 0, and probability of 1 being less than or equal to 1. I mean, that makes perfect sense. Now, if I want the quantile, now here's where things don't work out as an inverse function now, because you can see that I've got all these different values going on here. And because there's only 2 different possible values, the quantile function is going to go back and give me something reasonable. So, here, see, I've got, 0 through 10. So there's 11, 1, 2, 3, 4, 5. That's the middle, 1, 2, 3, 4. Yeah, so you can see that 0 through 0.5 get mapped to 0, 0.6 through 1 get mapped to 1 off of this. Now for random number generation, here I've got a random sequence of 0s and 1s. All right, well, wait a second. During previous videos, Aaron, you use the binomial family, not the Bernoulli family, and you've got binom on the screen right now. Why are you calling it Bernoulli distribution? All right, so if I have a bunch of 0s and 1s, and let's say I have n events. So previously I had 1 event, so I've got 1 event of 0s and 1s. Let's say I have 10, 20, 50, 2, 3, any positive integer value of events, and it's 0 and 1s, and now I'm interested not in 0 and 1 exactly, but in the sum of times that I get 1. So if I was to go through, take a binomial or a bunch of Bernoulli random variables and add them up. So look here, I think about this one. This is 10 Bernoulli random variables. If I were to add them up, I would have 1, 2, 3, 4, 5, 6. All right, so this is this value. The value would be 6. Here, the size is 10 because I've got 10 Bernoullis, and I have a probability of 1/2. So this is a way. If I was to convert this to binomial distribution, it would be 6 with size 10, probability 1/2. All right, so here, when I have a sequence of Bernoulli random variables, and I'm not interested in the actual sequence values, but just the sum of them, add them all up, the count of successes, then I can represent it in this manner. So here I've got the probability is that P that I have up here. Here is K is the number of successes. In this case, this would be a 6. And then here, this is the number of this is the probability of failure. So for this example, 1/2. Here, this is the number of failures. So here, this would be 4. 1, 2, 3, 4. And so this right here, this part that's highlighted blue, is exactly the probability of getting exactly this sequence. Exactly. But if I'm only concerned with the count of successes, the count of failures, I don't care about the order. I could have had all 6 be success, and then all the failures, or all the failures first, then all the successes, or any shuffling around of that. Well, this part here, this n choose k, accounts for the number of ways that I could shuffle around the zeros and ones and get a different representation. Okay, so we're using binomial distribution. Now, how does the binomial distribution connect Bernoulli trials to logistic regression? Okay, so how we get the connection there, let's say I have a row of data and I have particular predictor variable values. I have fixed predictor variable values, and I have exactly those observations, let's say 10 different times. And in those 10 times, I have a mixture of success or failures in terms of my logistic regression model. So for example, I have the same predictor variable values, but I have the first time is a success, second time is a failure, third time is success, fourth time is failure, fifth time is failure. Then I get 4 successes, and last time is a failure. All right, so because I have the repeated observation aspect, that one observation type, that level for the predictor variables, corresponds to 6 successes, 4 failures. And so I can convert that over, if I wanted to, depending on how I want to code my data, I can put this into into the logistic regression fitting, the GLM function, as a binomial random variable counts instead for my target variable. If I wanted to do that, I could also do the proportion of successes, like 6 over 10. That's another way I can do that. GLM will spit like warning messages at you, but it's okay as long as you know what's up. All right, so here, just to extend this, let's go ahead and say now I have a size 10. So now I'm interested in the probability of getting 0 successes, or 1 success, 2 success, 3 success, or all 10 successes when I have 10 events going on, and I have a probability of 50-50 on each individual event. And so now I have a probability distribution function in this manner. All right, and you can see that in the middle, on this particular one, because of how I built it up, we can see that we've got the maximum probability there. That'd be 1, 2, 3, 4, 5, 6. We can see 6 is the highest. All right, so now here's the cumulative distribution function, and you can see that the numbers are only getting bigger as I go from left to right, and going from from just a little bit above 0 all the way up to 1. Now the quantile, if I want to take from 0 to 0.1 to 0.2 to 0.3 all the way up to 1, and I want to pseudo inverse the going backwards, here is the values I'm going to get. And you'll notice that it's not a true inverse function off of this. We see 4, 5, and 6 are appearing multiple times. And we can also do random number generation. Okay, so now that's the binomial distribution. And so so we're going to model the probability of an outcome, success or failure, as a function of the predictor variables. And we're going to use the log odds, or log it, transformation for this. So we actually want probability, because probabilities are much easier for humans to interpret, but the math doesn't work out so well. So instead of going directly at probabilities, I'm going to take a function that has an inverse from probabilities to that function and work it out that way. So here is the probability that I'm actually interested in, but the math doesn't work out like I would like it because it only goes from 0 to 1. And mathematically, it would be better if we could go from, you know, from like 0 to infinity. That'd be great. That'd be better. But it would be best if I could go from negative infinity to positive infinity. Well, to do that, if I go odds, here I'm going from 0 to infinity, but here I go from the entire real line of negative infinity to positive infinity. So I've got the full range of possible numbers to work with. This works out that I don't have to force anything weird when I fit my model. All right, so we're going to say that the log odds is equal to the add-ins that we get when I take predictor variable times coefficients, and then add the intercept term. So I have, here's the part that's coming from the parameters and observed data, and here's what is being estimated by. Now, remember, we're taking the approach that we're estimating the expected value of the probability. You'll notice that there's no epsilon in there because we're not concerned with individual fluctuations like we would be if I was doing standard linear regression. All right, so here I could go through and solve for p very easily to get this equation. And if this is p, then 1 minus p, the probability of failure, is very direct also. Okay, so now to get the likelihood function off of this, what I can do, here's the p, here is 1 minus p. If I go back up to that function I have here, well, there's a p, there's 1 minus p. I can go in and put those values in there to work this out. So remember, my likelihood function on pencil and paper is the same as my probability function, but the interpretation of individual entries as a variable or a constant switches. All right, so here's my likelihood function. All right, so in my regular old probability distribution, I have the probability distribution function. I have the value of x is the random variable. That's the variable of the function. And I have my parameters as a constant. Well, what I'm going to do is, well, what if I switched it? If I switched it, then the random variables are now constants because they're observed data points. There's nothing random about them anymore after I collect my data. So I'm going to treat my observed data as the x. And now I'm going to treat the parameters that were constants. Now they're the unknown variable because they're what I want to estimate. And we're going to write this a little bit more compact like this. All right, so what we want to do, we want to estimate the coefficients, those betas, that give me a good fit, based off of my data. All right, well, here is the likelihood function. I can rewrite it in this manner. All right, so here is likelihood. Now focus on the right-hand side. The right-hand side, I have a whole collection of observations going on, and I have a vector of parameters. Okay, well, what I could do is if I have independence between my observations, I can change this into the product of individual observations inside the probability distribution function. So this is the product of that distribution for each individual observation. And I can rewrite it like this. Now I'm assuming that independent, identically distributed, with respect to the whole regression model aspect, independent, identically distributed. Okay, so now I have a product of a whole bunch of probability distribution functions is equal to my likelihood. All right, so now I can go in, I can go, well, these are the individual observations, right? So I can replace this with the Bernoulli distribution aspect like that. So now, and this should be y sub, this j should be subscript on the y. That's an error on my part. All right, and so now I look at that. Well, you know what? I'm looking at that. I could simplify that further. What I could do is replace the p's with this p here, replace the 1 minus p with the 1 minus p here, and then I can simplify that. All right, so then I plug in the p and the 1 minus p. And now you'll notice, well, 1's really simple for multiplication, so I don't really need to worry about this part of the numerator. I notice I've got the same denominator on both sides of it. Well, hey, that's interesting. So it, regardless of what y is, I get the same denominator on here. Oh, that should be a j. And so I've got this. And so now I'm left with this part here. And so I'm just going to, do the appropriate thing with an exponent on the exponent. All right, so I've got that. And so things are coming together. All right, so now I see I've got my likelihood function is equal to this. Now I see that I've got a lot of multiplication going on. And in general, when we're doing math, when we're doing our calculus, we don't like products. If I have a bunch of products, I might want to be able to convert that to a use logarithm to make that into an addition. Okay, so we'll go ahead and do that. Now, why do I do that? Because it makes the calculus easier. All right, so I'll take the log of both sides. Well, logarithms convert multiplication to addition. And so, boom, I've got this. Now, you'll notice the next thing I'm going to do is, just go through and subtract the logarithms. And, I'll just keep on working through this. All right, so I have a log of an exponential. That cancels out. So I've got that. And I've got a negative log of this business over here. Okay, well, I notice I've got a sum of y's and a sum of observations. So here, this is just going to be n times y bar for this summation. And the summation I get here is going to be n times the product of x and y. Okay, and so that's why I put the parenthesis in the bar. I tried to get the wide bar on there, but it didn't work out. All right, so maximum likelihood estimation. Ideally, my estimate of the coefficients would be whatever values of the betas will maximize this whole thing. And you'll notice I'm doing simple linear regression just to make it easier on me. Unfortunately, there's no closed formula for this estimate. I've worked out all this math, and you know what? More than likely, I'm not going to be able to do this calculus. It's not going to work out. It's, just too much. And so what we're going to do instead is we're going to use an optimization program. We're going to let the computer estimate it for us, and that's going to be close enough for our work, assuming it converges. And so what I'm going to do is we're going to approach this in another manner. I'm going to rewrite this in another way. And you'll see that this is a little bit cleaner of a presentation than what I had. And so this is a better presentation for the computer to be working with. All right, so for maximum likelihood estimation, I'm not going to do this by hand. I'm not going to do this manually. Potentially, in theory, I could, but you know what? It's not going to be worth it. Give it to the computer, have the computer work it out. In simple linear regression, or just any old linear regression, we have matrix formulas that make this really easy, that potentially, if I was stranded on a desert island without a computer, I could do the calculations on my own, with pencil and paper. More than likely, I'm not going to be able to do that if I'm doing logistic regression. All right, so what we're going to do, we're going to use the GLM function, generalized linear model. We're going to set family equal to the binomial function, and we're just going to let it do the work for us, and it's going to spit out for us immediately. All right, so here I am just setting up my workspace. I'm loading the Regression package to do piping, getting rid of some variable, or make sure it doesn't print up too many digits, clearing everything going on. And here is my data set that I'm going to use. And so now I have fit a simple logistic regression model using age to predict chronic heart disease. All right. And you'll notice I use the binomial family for this. If I did not specify the binomial family or another family, the GLM function would assume I was doing Gaussian and would have gone straight to standard linear regression instead of logistic regression, and my model would not make sense. All right, so for your homework, what I want you to do I want you to write out this likelihood function using the Cauchy link function. So here, this is the Cauchy distribution, and replace the p's with Cauchy distribution, version of what we talked about, and just look at what happens. Write down on paper what you would do if you were going to take the derivative, and pretend you're going to take the derivative. I want you to look at it really hard and realize, oh crud, I don't want to do this. This is going to be really hard. If I have 1,000 data points, this is going to be practically impossible for me to do with pencil and paper. You know what? I'll let the computer do this. So the point of this homework is that you can't do it. But I want you to go up to the edge as far as you can and look down and see, oh, wow, this is something I don't want to do. You have convinced me. Let the computer do it. All right, that's all I've got for you. Life is short. Do math.